The work that Roger Penrose and I did between 1965 and 1970 showed that, according to general relativity, there must be a singularity or infinite density within the black hole. This is rather like the Big Bang at the beginning of time, only it would be an end of time for the collapsing body and the astronaut. At the singularity, the laws of science and our ability to predict the future would break down. However, any observer who remained outside the black hole would not be affected by this failure of predictability because neither light nor any signal can reach them from the singularity. This remarkable fact led Roger Penrose to propose the cosmic censorship hypothesis, which might be paraphrased as God abhors a naked singularity, all this in quotes. In other words, the singularities produced by the black gravitational collapse occur only in places like black holes, where they are decently hidden from the outside view by an event horizon. Strictly, this is what is known as the weak cosmic censorship hypothesis. Protect observers who remain outside the black hole from the consequences of breakdown of predictability that occurs at the singularity. But it does nothing at all for the poor unfortunate astronaut who falls into the hole. Shouldn't God protect his modesty as well? There are some solutions of the equation of general relativity in which it is possible for our astronaut to see a naked singularity. He may be able to avoid hitting the singularity and instead fall through a wormhole, in quotes, and come out in another region of the universe. This would offer great possibilities for travel in space and time, but unfortunately it seems that the solutions may all be highly unstable. The least disturbance, such as the presence of an astronaut, might change them so that the astronaut cannot see the singularity until he hits it and his time comes to an end. In other words, the singularity always lies in his future and never in his past. I don't understand this completely, but okay, maybe not be the most important thing here. The strong version of the cosmic censorship hypothesis states that in a realistic solution, the singularities always lie either entirely in the future, like the singularities of the gravitational collapse, or entirely in the past, like the Big Bang. It is greatly to be hoped that some version of the censorship hypothesis holds, because close to naked singularities, it may be possible to travel into the past. While this would be fine for writers of science fiction, it would mean that no one's life would ever be safe. Someone might go into the past and kill your father or mother before you were conceived. In a gravitational collapse to form a black hole, the movements would be damped by the emission of gravitational waves. One would therefore expect that it would not be too long before the black hole would settle down to a stationary state. It was generally supposed that this final stationary state would depend on the details of the body that had collapsed to form the black hole. The black hole might have any shape or size, and its shape may not even be fixed but instead be pulsating. However, in 1967, the study of black holes was revolutionized by a paper written in Dublin by Werner Israel. Israel showed that any black hole that is not rotating must be perfectly round or spherical. Its size, moreover, would depend only on its mass. It could, in fact, be described by a particular solution of Einstein's equation that had been known since 1917, when it had been found by Carl Schwarzschild shortly after the discovery of general relativity. At first, Israel's result was interpreted by many people, including Israel himself, as evidence that black holes would form only from the collapse of bodies that were perfectly round or spherical. As no real body would be perfectly spherical, this means that in general, gravitational collapse would lead to naked singularities. There was, however, a different interpretation of Israel's result, which was advocated by Roger Penrose and John Wheeler in particular. This was that a black hole should behave like a ball of fluid. Although a body might start off in an unspherical state, as it collapsed to form a black hole, it would settle down to a spherical state due to the emission of gravitational waves. Further calculations supported this view, and it came to be adopted generally. Israel's result had dealt only with the case of black holes formed by non-rotating bodies. On the analogy with a ball of fluid, one would expect that a black hole made by the collapse of a rotating body would not be perfectly round. It would have a bulge around the equator caused by the effect of rotation. We observe a small bulge like this in the sun, caused by its rotation once every 25 days or so. In 1963, Roy Kerr, a New Zealander, had found a set of black hole solutions of the equations of general relativity more general than the Schwarzschild solutions. These, in quotes, Kerr black holes rotate at a constant rate, their size and shape depending only on their masses and rate of rotation. If the rotation was zero, the black hole was perfectly round and the solution was identical to the Schwarzschild solution. But if the rotation was non-zero, the black hole bulged outward near its equator. It was therefore natural to conjecture that a rotating body collapsing to form a black hole would end up in a state described by the Kerr solution. In 1970, a colleague and fellow research student of mine, Brandon Carter, took the first step toward proving this conjecture. He showed that provided a stationary rotating black hole had an axis of symmetry like a spinning top, its size and shape would depend only on its mass and rate of rotation. Then in 1971, I proved that any stationary rotating black hole would indeed have such an axis of symmetry.
We have a very good chance of getting on the confirmed list.
Finally, in 1973, David Robinson at King's College London used Carter and my results to show that the conjecture had been correct. Such a black hole had indeed to be the Kerr solution. Okay, I'm reading out this book. Just because you read a book doesn't mean you understand anything. This is complicated stuff, but to the extent that you can remember these names and that there are some rotating black holes and some possibly non-rotating black holes, I think the job is done. So after gravitational collapse, a black hole must settle down into a state in which it could be rotating but not pulsating. Moreover, its size and shape would depend only on its mass and rate of rotation and not on the nature of the body from which that had collapsed to form it. This result became known by a maxim: a black hole has no hair. These scientists who came up with these maxims need to be lined up and something should be done to them. God abhors naked singularities, a black hole has no hair, bald black holes, crazy people. Nevertheless, it means that a very large amount of information about the body that has collapsed must be lost when a black hole is formed, because afterwards all we can possibly measure about the body is its mass and rate of rotation. That is true. There is initially some object, possibly like a star or something, which can be defined by a lot more quantities, but finally when the black hole is formed, it's defined by simply two quantities: its mass and its rate of rotation. The significance of this will be seen in the next lecture. The no-hair theorem is also of great practical importance because it so greatly restricts the possible types of black holes. One can therefore make detailed models of objects that might contain black holes and compare the predictions with of the models with observations. Black holes are one of only a fairly small number of cases in the history of science where a theory was developed in great detail as a mathematical model before there was any evidence from observations that it was correct. Indeed, this used to be the main argument of opponents of black holes. How could one believe in objects for which the only evidence was calculations based on the dubious theory of general relativity? I wonder what other cases are there where the theory was so much more well developed before there was any experimental observation. Possibly, if string theory comes true, then there must be some experimental evidence that comes much later, so that's a possibility. I wonder what else. Of course, the Friedman solution was also like that, right? Earlier when we studied about Hubble, finding the experimental evidence. I think Friedman it was who had actually, Friedman or someone else, whoever it was, I need to look up the name, go back and look up the name, but he had predicted that such a thing would happen, that galaxies far away would be receding, right? The redshift of light and so on and so forth. So that, I don't know what other examples are there where theory is developed much before the empirical science. Okay, anyway, in 1963, however, Martin Schmidt, an astronomer at the Mount Palomar Observatory in California, found a faint star-like object in the direction of the source of radio waves called 3C273. That is, source number 273 in the third Cambridge catalogue of radio sources. When he measured the redshift of the object, he found it was too large to be caused by a gravitational field. If it had been a gravitational redshift, the object would have to be so massive and so near us that it would disturb the orbits of planets in the solar system. This suggested that the redshift was instead caused by the expansion of the universe, which in turn meant that the object was very long way away. And to be visible at such a great distance, the object must be very bright and must be emitting a huge amount of energy. The only mechanism people could think of that would produce such large quantities of energy seemed to be the gravitational collapse of not just a star but of the whole central region of a galaxy. A number of other similar quasi-stellar objects or quasars have since been discovered, all with large redshifts. But they are all too far away and too difficult to observe to provide conclusive evidence of black holes. Remember that this book was written in the 1970s or 80s or 90s perhaps. I'm sure things have changed now and that quasars can be observed more easily, but still they are more difficult than stars to observe, I guess. Further encouragement of the existence of black holes came in 1967 with the discovery by a research student at Cambridge, Jocelyn Bell, of some objects in the sky that were emitting regular pulses of radio waves. Continue from a little way behind. Further encouragement for the existence of black holes came in 1967 with the discovery by a research student at Cambridge, Jocelyn Bell, of some objects in the sky that were emitting regular pulses of radio waves. At first, Jocelyn and her supervisor, Anthony Hewish, thought that they had made contact with an alien civilization in the galaxy. Indeed, at the seminar in which they announced their discovery, I remember that they called the first four sources to be found LGM1, LGM2, LGM3, LGM4.
It means little green man.
LGM standing for little green man.
It means little green man. Can confirm, my dad told me that a few days ago. It was funny, and I still think that there are little green men out in this universe who I would like to personally visit and brutally murder.
No. Brutally make merry with.
My bad, I have dark humor.
Yes. In the end, however, they and everyone else came to the less romantic conclusion that these objects, which were given the name pulsars, were in fact just rotating neutron stars. They were emitting pulses of radio waves because a complicated interaction between their magnetic fields and surrounding matter. This book was published by Jacob Books and there are so many printing errors. You can't believe it. Here it says a complicated indirection between their magnetic fields and surrounding matter. And I have to think of what that word is. It's a complicated interaction between their magnetic fields and surrounding matter. Anyway, this is bad news for writers of space westerns, but very hopeful for the small number of us who believed in black holes at that time. It was the first possible evidence that neutron stars existed. A neutron star has a radius of about 10 miles, only a few times the critical radius at which a star becomes a black hole. If a star could collapse to such a small size, it was not unreasonable to expect that other stars could collapse to even smaller size and become black holes. How could we hope to detect a black hole as by its very definition it does not emit any light? It might be a bit like looking for a black cat in a coal cellar. This analogy is apt. Trying to look for a black hole is a little bit like looking for a black cat in a coal cellar. At least the black cat has eyes. Fortunately, there is a way, since as John Mitchell pointed out in his pioneering paper in 1783, a black hole still exerts a gravitational force on nearby objects. Astronomers have observed a number of systems in which two stars orbit around each other, attracted towards each other by gravity. They also observe systems in which there is only one visible star that is orbiting around some unseen companion. Do you listen to this? Oi. Astronomers have observed binary star systems, but they have also observed binary star systems where one star is orbiting around an unseen companion. So what should that unseen companion be?
Black hole.
Black hole, possibly. And the star is going to eventually fall into the trap of the black hole. It's on its course to being part of the black hole.
Let me search up the largest single object of the universe.
Of course, one cannot, of course, immediately conclude the companion is a black hole. Okay, it might merely be a star that is too faint to be seen. However, some of these systems, like the one called Cygnus X1, are also strong sources of X-rays. The best explanation for this phenomena is that the X-rays are generated by matter that has been blown off the surface by the visible star. As it falls towards the unseen companion, it develops a spiral motion rather like water running out of a bath, and it gets very hot, emitting X-rays. For this mechanism to work, the unseen object has to be very small, like a white dwarf, neutron star, or a black hole. Now, from the observed motion of the visible star, one can determine the lowest possible mass of the unseen object. In the case of Cygnus X1, this is about 6 times the mass of the Sun. According to Chandrasekhar result, this is too much for an unseen object to be a white dwarf. It is also too large a mass to be a neutron star. It seems therefore that it must be a black hole. There are other models to explain Cygnus X1 that do not include a black hole, but they are all rather far-fetched. A black hole seems to be the only real natural explanation of the observations. Despite this, I have a bet with Kip Thorne of the California Institute of Technology, or Caltech, that in fact Cygnus X1 does not contain a black hole. This is a form of insurance policy for me. I have done a lot of work on black holes, and it would all be wasted if it turned out that black holes do not exist. But in that case, I would have a consolation of winning a bet, which would bring me 4 years of the magazine Private Eye. I don't know what happened to this bet. If black holes do exist, Kip will only get 1 year of Penthouse, because when we made the bet in 1975, we were 80% certain that Cygnus was a black hole. By now, I would say that we are about 95% certain, but the bet is yet to be settled. There is evidence for black holes in a number of other galaxy systems in our galaxy. There is evidence for black holes in a number of other systems in our galaxy. So it means that there could be multiple black holes in the galaxy itself. And for much larger black holes at the center of galaxies, other galaxies and quasars. Again, I need to go back and see what these quasars are. Quasi-stellar objects.
Yep, quasi-stellar objects.
But so these are huge objects. A number of similar quasi-stellar objects have been observed. So quasi-stellar objects.
Apparently, there are things called galactic farts.
Galactic farts.
The largest galactic fart is named after Fermi.
Okay.
Enrico Fermi.
Was he supposed to be a massive farter?
No.
Okay.
It was used during using the Fermi space. They were seen using the Fermi space telescope.
Okay. Okay. There is evidence for black holes in a number of other systems in our galaxy, and for much larger black holes at the center of other galaxies and quasars. One can also consider the possibility that there might be black holes with masses much less than that of the Sun. Such black holes could not form by gravitational collapse because their masses are below the Chandrasekhar mass limits. Stars of this low mass can support themselves against the force of gravity even when they have exhausted their nuclear fuel. So low mass black holes could form only if the matter were compressed to enormous densities by very large external pressures. Such conditions would occur in a very big hydrogen bomb. The physicist John Wheeler once calculated that if one took all the heavy water in all of the oceans of the world, one could build a hydrogen bomb that would compress matter at the center so much that a black hole would be created. Unfortunately, however, there would be no one left to observe it. A more practical possibility is that such low mass black holes might have been formed in the high temperatures and pressures in the very early universe. Black holes could have been formed if the early universe had not been perfectly smooth and uniform, because then a small region that was denser than average could be compressed in this way to form a black hole. But we know that there must have been some irregularities, because otherwise the matter in the universe would still be perfectly uniform, distributed at the present epoch, instead of being clumped together in galaxies and stars. Whether or not the irregularities required to account for the stars and galaxies would have led to the formation of a significant number of these primordial black holes, these small mass black holes, depends on the details of the conditions in the early universe. So if we could determine how many primordial black holes there are now, we would learn a lot about the very early stages of the universe. Primordial black holes with masses of more than 1,000 million tons, the mass of a large mountain, could be detected only by their gravitational influence on other visible matter or on the expansion of the universe. However, as we shall learn in the next lecture, black holes are not really black after all. They glow like a hot body, and the smaller they are, the more they glow. So paradoxically, smaller black holes might actually turn out to be easier to detect than larger black holes.